I'm Zong and I'm demoing my FYP. The problem that we'll be discussing here is virtual machine placements. So as shown in the diagrams, when a user requests a service from the cloud will create a virtual machines for the user, and the virtual machine will be hosted on a physical machines. So the virtual machine placement is actually how we allocate or host the virtual machines on which physical machines. And it can be formulated as a bin packing problems where there are items of different sizes and infinity amount of bins, and we are to allocate the item into the bins such that the total item allocated to the bin, the size doesn't exceed the capacity. And the objective here is to minimize the total number of bins used. The exact variance of bin packing problems that fit the virtual machine placement is mean usage time, dynamic vector, bin packings. So there are three keywords. First is the vector. It means that items have different dimensions and each dimension may have different sizes. Next, dynamic means that items have arrival time and departure times. Item may arrive at any time and depart at any time after it. And last is the mean usage time, which means that the objective is not minimize the number of bins used, but rather minimize the total usage time of all bins. A bin is said to be active if and only if there are at least one item allocated to it at that point of time. Next, in the report, I also proved that the variance of it is also a NP-hard problem, which I will not be discussed here. Next, I will be talking about the experiment setup. So I uses Microsoft Azure datasets and set up 27 scenarios out of it, and I run each scenario against each algorithms. So algorithms is categorized into three categories based on the amount of information known to the algorithms. So first is online non-correlate. This means that the algorithm do not know any of the future informations, which means that when an item arrive, it do not know what is the departure times, and also it do not know what is the future arrival items. And these are the algorithms under this category. So next is online correlate, which means that when an item arrives, it knows the departure times. However, it still do not know what is the future items. In offline correlate, it means that we know the entire item distributions, which means that at any point of time we know what is the future item, we know what is the departure time of the arriving item. Next, I will be showing how I analyze the data. So after running the algorithms on each scenario, we can get the total number of machines or the bins at any point of time, and we can plot the graph on the right. With this, we can calculate the total usage times of all bins for each algorithm. Instead of using the raw number of bin usage time, because each scenario may have difference, we use the ratios instead, which is the ratios of the total usage times against over the lower bounds of each scenario. And the lower bound is divided by the sum of the maximum item weight at each time. As such, we have 27 ratios for each algorithms, and we can plot a box plot for each algorithms which consolidate the 27 scenarios, and we can compare the algorithms. So we can see from the box plot, the max best fit is the best amongst all the best fits. So similarly, the online non-correct, we can do the similar analysis and get this box plot. So we can see that first fits actually perform the best and next fit perform the worst. The similar for online correct, we can see that classified by departure time and closest remaining time perform quite well. Both of these have similar characteristics that they group items of similar departure times together. It shows that this algorithm seems to perform quite well. For offline correct, since we have only one algorithm, we compare it against the best non-correct and the best offline correct. As we can see, the more information you know, the better it becomes, which is expected. And that ends the demo. Thank you.